For elliptic equations, let's do another analysis. Again, using Fourier. So for elliptic equations, we have the second order derivative of u plus f is equal to 0. So here, let's expand f using Fourier series. K goes from minus infinity to infinity, f hat of k times e to the j kx. All right. So if we also expand the solution using Fourier series, u hat of k e to the j kx, and the derivative works the same, right? So the partial square u partial x square would be equal to summation of minus infinity to infinity. U hat of k stays because it's not a function of x, and taking twice derivative, we get minus k squared. Each time you take a derivative, you get a jk. So jk squared is equal to minus k squared times e to the jkx. Now you add this and this, they have to sum to 0. Therefore, the corresponding terms has to sum up to 0. So f hat of k minus k squared times u hat of k has to be 0 for all k, right? So the rest is doing division. U hat of k would be equal to 1 over k squared times f hat of k. Thinking about different k's corresponding to different qualitative components in the solution u and in the forcing function f or source term f. Would you expect f to be more oscillatory or smooth or smoother than u? Okay, so given an f, would you expect the solution u to be smoother or more oscillatory? Smoother, right? Because the larger case gets multiplied by a smaller coefficient. The only term that is going to be as large as the original f is the k equal to plus minus 1 term, right? How about the k equal to 0 term? Doesn't seem to work, right? Okay, so this equation only had solution when what? F hat 0 is equal to 0, right? So okay, so one way to think of the solution to this equation is to go back to our original, or go back to the last slide. Think of the equation with a time derivative, right? So instead of this is equal to 0, you set this to a time derivative, partial u partial t, and if you have this time derivative, you evolve that equation to infinity, right? You solve that equation to infinity, and instead of having no source term, you have a source term. So you have a function that keeps adding heat into the equation, keeps adding to the solution as time evolves. What is the final solution? And thinking from that physical perspective, you know that f cannot have any constant term, because if that is the case, the solution is going to either keep becoming larger and larger and larger, goes to infinity, or it keeps becoming smaller, 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 and goes to minus infinity. So f has to have no f hat 0 component. Now, this is a type of elliptic equation. Elliptic equation is characteristic for having no time. Okay, and this equation, as I said, if you add a partial square u partial y squared term, it'll look the same, except for the Fourier series has to be two-dimensional Fourier series, right? But like in this equation, if you change anything on f, if you perturb f, the effect is going to be felt everywhere, right? And the difference between previous case we also said the effect is going to be felt everywhere, but this case is really everywhere, not just after a particular time, because there is no time. If you introduce another variable, let's say y is not a time, right? I mean, if you change anything at any xy location, it'll be felt at every xy location. As opposed to the previous case, if you put a perturbation at a particular xt location, it'll be only felt at xt locations where t is after that perturbation time. So elliptic equation, if I have a domain xy, a domain is like this. The domain of influence is anywhere in the domain, no matter where the perturbation is.